Okay, so we've seen what happens when we have issues with our bounds going to infinity. But I just said issues, right? So anytime we have an issue, it doesn't have to just go to infinity. It could be something else. Like in this instance, if it has an unbounded integrand, which means I have an open interval. Do you see that? There's an open interval. There's a parenthesis on that A, so that means it is an open interval, and that's what we're going for. So if I'm looking at this, and in this particular instance, A is the issue. That is the one that I'm taking a limit of, but look at what's happening. I'm going to take the limit here as C approaches A from the right, and I'm approaching A from the right here of my integral of C to B. I don't know why I'm rewriting this. Apparently I just really liked it. Because if I'm approaching C, now think about this for a second. A is the issue, but it's on the bottom, right? So it's the lower bound. That's why it's so important to write your bounds in order. If you have a lower bound A that I'm looking at, so I'm just taking some arbitrary C and I'm approaching this A. But look where I'm approaching from. From the right, right? So I have to stick within this bound. This is the bounds that I'm given, small to big. So if I'm going toward this value, I'm going from my big value to my small value, and that's approaching from the right. Making sense now? Okay, so, pardon me, if I have an open bound, my open interval is the top bound there, right? If I'm looking at this, so B is the issue. Then I'm going to approach, whenever I plug in this C value, I'm approaching B from the left because I'm going from small to big. So from small to big, I'm approaching it from the left. Do you see that? That's how you know if you're approaching from the right or the left. So if the one of those bounds cause an issue, like a 0 in the denominator, right? These are the kinds of things that we're looking for. Then you have to take the limit and take that one out, but you approach it from whatever side you need to because it's an actual number there. All right? Okay, so let's scoot this up a little bit here. What if I have a closed interval, however, there is an interior point P that has an issue? All right, so P, some value on the inside here, P is on the issue. Wait, P is the issue on the inside of the interval. So you have to count for that issue. You just split it up. See how this is? So I'm going to approach P from the left and I'm approaching P from the right as I'm looking at this because C that we have and D that we have down there. All right? Okay. And again, if you have a value, it converges. If it doesn't, then it diverges, and you're looking at your positive and negative infinity for that again. So the same converge, diverge situation is happening, but instead of it just being infinity, you have to take a closer look. Because, ooh, do one of my bounds cause an issue? Okay, that makes it different, right? So you have to pay closer attention because it's not going to jump out at you like the infinity does. So you have to tune in a little bit more with this. Okay, we're going to work some examples, so here we go.